Hi, good morning, everyone. Thank you for being here. I'm Luana. I just obtained my PhD from the Electrical Engineering Department at UPenn. I'm now a research fellow here at Simons. I'm going to be a postdoc at FODSI in the spring, and then I'll be joining the Applied Math Department at Hopkins next summer. And today I want to talk about some of the research that I did on machine learning on large-scale graphs. So to motivate my talk, I have to answer two preliminary questions, which are the why and the how. The why is, why do we care about machine learning on large-scale graphs? And that question has a relatively easy answer. The answer being that the need to process information on very large graphs arises in a wide range of applications. So for example, I have two examples of applications where this need arises. One of them is this product similarity graph, where the nodes represent products, the edge weights represent product similarities, and we can define a signal on top of this graph, which is given by the ratings that some user or consumer has given to some of these products. And then given some of these ratings, what we want is we want to leverage the graph structure to fill in the missing ratings and make pointed product recommendations, right? Another example is this problem here on the right, where we have a graph that is given by a team of robots or agents that we want to control in a distributed manner. And what we want them to do here is we want them to flux, so fly at the same velocity while avoiding collisions. But the catch here is that communications are limited by proximity because we want to limit interference. And so any control policy that we come up with has to respect this information structure that is given by this graph. So both of these problems are examples of problems where we can motivate the use of learning, and learning has indeed been shown to outperform other existing solutions. And there are also examples of problems where they become more interesting as these graphs increase, right? So if we have a lot of, like, say, in the order of thousands of products, in the order of hundreds of robots. But the issue is that machine learning models become harder to train or to learn for these problems as these graphs grow. We know that machine learning works well in moderately sized graphs, but it's harder to train them on these large graphs. Now, the how question, which is how do we do machine learning on large scale graphs, also has a relatively easy answer. And the answer from that comes from the ample amount of empirical and theoretical evidence to support using neural networks. The issue is that standard, by which I mean fully connected neural networks, they're not scalable. The neural networks that we know are scalable are convolutional neural networks that we use to process time signals and images, and that we know scale well to large data of that type. However, convolutional neural networks only operate on regular grid-like data, such as this data here on the left, while the information that we want to process lies on irregular structures better modeled by these graphs, by graphs such as the one on the right? And so this observation provides both a challenge and a solution, right? The challenge is that we have to find some way to extend convolutions and convolutional neural networks to this type of data. The solution is that people have been doing that for half a decade now or so by defining graph convolutions and graph neural networks. So in my research, I am interested in two research questions. The first one is that we have empirically observed that graph neural networks scale, but we don't know why they do. And the second question is whether we can leverage the success of GNNs on moderate-sized graphs to generate success at a large scale. And I'll be more clear about this point in a couple of minutes. And to answer both of these questions, we should turn to graph limits. And why should we turn to graph limits? Well, because limits, they reveal the intrinsic dimension of the data, which is typically smaller than the graph size. And this would help explain why GNNs scale well to large data, large graph data. And second, because if we're able to characterize the convergence of graphs to this graph limit, maybe we'll learn things that will both help us understand whether GNNs converge to a limit on these graphs, and maybe will tell us something that will, can be exploited to facilitate the training of GNNs for these large-scale graph applications. Now, as we have heard about extensively last week, graphs indeed have limit objects that effectively limit their dimensionality, and one such limit object is the graphon, of which I have an example here on this slide of an Erdős-Renyi graphon. And this graphon can be thought of as a graph with an uncountable number of nodes. It's a kernel, a bounded symmetric kernel. And what we see when we look at sequences of graphs that converge to graphon is that the overall structure of these graphs is also converging to the overall structure of the graphon. And in this case here, we can really see that if we look at the 200 node graph and at the limit graphon, right? The structures become increasingly similar. I should say that this is a very simple example of graphon, but this convergence of structure and many other properties holds for more interesting examples of graphs and graphons as well. Now, it's good to know that graphs converge to a limit, right? And in this case, we're focusing on the graphon. But this convergence of graphs doesn't necessarily imply that convolutions and therefore that neural networks converge to limits on the limits of these graphs, right, on the graphon. And the reason for that is that, convergence of convolutions in Euclidean domains is actually related to sampling. And sampling is very regular, it depends on geometry, and so it won't translate verbatim to graphs, right? Because they have these irregular structures, as we can see here from the sequence of product graphs. And so whether graph convolutions and graph neural networks converge to limit objects on the graphon is a result that needs to be established. So in my research, I did prove that graph convolutions and therefore graph neural networks converge to limit objects on graphons. And this result is then what provides the answer to the two research questions that I posed earlier, right? So the answer to the fact that GNNs scale well empirically, like what explains that is that graph convolutions and GNNs have well-defined limits on graphons, graphon convolutions, and graphon neural networks. And this is an asymptotic convergence result, but I also developed the finite sample version of this result. And essentially what this finite sample version says is that if I have a graph neural network with same parameters, and I run it on one graph GN and on one graph GM, and these graphs are related through the same graphon, right? They are either sampled from the same graphon or parts of sequences that converge to the same graphon. Then the difference between the outputs of the GNNs in these two graphs is small. What this can be interpreted to mean is that GNNs are transferable across these graphs. And so we can use that to generate success on large-scale graphs by leveraging the success that GNNs have on moderate-sized graphs, by training GNNs on these smaller graphs, and then transferring them to these large-scale graphs with small error. So we're able to upper bound this error. So I'm not going to go into the details of the theorems here. I do want to say that I will be giving a talk, a longer version of this talk in the next graph workshop. But I do want to say that there's an interesting results that we uncovered from this transferability analysis. And this result that we uncover is that there is a trade-off between the spectral discriminability and the transferability of these linear convolutional filters that make up the layers of the GNN. And I'm going to try to explain using this plot here why that happens. So what I'm showing here on the slide is in red. So the red curve is the spectral or frequency response of this graph convolutional filter. And in green, I have the eigenvalues of a graph GN, and in blue, the eigenvalues of a graph GM that are associated with the same graphon. So say that these are two graphs that are in a sequence that converges to a graphon, and they have different sizes. And so from graphon theory, we know that the eigenvalues, so the spectrum of these graphs converges to the spectrum of the graphon. And the spectrum of the graphon has the property that it is contained in this -1, interval, and it's, it's infinite dimensional, so it accumulates near zero and only near zero. So what's happening here is that if you have filters that are very sharp, close to zero, because these eigenvalues accumulate, they might get scrambled. And so what could happen is that because the filter is sharp, it might amplify eigenvalues from the green graph and the blue graph very differently. I mean, eigenvalues associated with the same eigenvalue index, right? So essentially the same frequency. And what this will cause will be a mismatch. So it will create a transferability error here. And if you compound this error for all of these eigenvalues, then what you'll have is a larger transferability error. So what you need to have to ensure that these filters and therefore the GNNs that they transfer well is we need these filters to be flat near zero. And I say that this creates a trade-off in terms of spectral discriminability, because if they have to be flat near zero, what this means is that now these filters can't discriminate between eigenvalues close to zero, right? They can select any of these eigenvalues. So we can expect, this trade-off to be inherited by graph neural networks, because graph neural networks are just layers where each layer has a graph convolution and a pointwise nonlinearity. We have a hypothesis for why this trade-off is alleviated in GNNs, but again, I will elaborate on that in the longer version of this talk. So let me just conclude by saying that transferability is, useful, and it's also applicable in practice. And in particular, you do see that in those two application examples that I mentioned earlier in this talk. So in the recommendation system example, right? So again, here, remember, we have this product graph. We have some ratings, and we want to fill in the missing ratings. So in this setting here, what I want to do is I want to train a GNN to fill in the missing ratings on the smaller graph, and then use it to fill in missing ratings on this larger graph, right? So I do that, and then what I'm considering there on that plot on the right is the mean squared error of prediction. And when I'm plotting on the y-axis is the difference between the mean squared error on the small graph and on the large graph. But the mean squared error that is attained by the same GNN, and this GNN is trained here, okay? The target graph always has 4,000 movies here. The products are movies. And the training graph, the size of this training graph is in the x-axis here. So what we see when we train these linear graph convolutional filters and GNNs is that the difference between the outputs of the GNN, so the transferability error between the target and the training graph, decreases as the size of the training graph increases. So we observe this transferability behavior. And again, it's interesting to see that the GNN, which is these two curves here, the orange and the green one, has lower transferability error than filters. And then looking at the second problem now, where we have now our team of agents. We want a GNN to learn a control policy in order for these agents to flock. Here we have the same setting. We want to train it for a small number of agents, execute it on a network with 100 agents. And here I'm plotting the difference between the costs that are achieved by the GNN, by the same GNN on the training graph and on the target graph. This cost is a weighting of velocity differences and collision penalties. And what we see here is that we increase the number of agents in the training graph, the transferability error also decreases. So let me stop here. I just want to conclude by saying that I am interested in further applications of these results and of graph neural networks to other graph problems, in particular graph problems where existing algorithms take a long time on very large graphs, and where we can maybe leverage this transferability property of GNNs to train GNNs in a subsampled version of these graphs, execute on the large graph. I'm also interested in extending these results to sparser graph models, right? Because the graphon is dense. And with that, let me stop here. Thank you very much.
Thank you very much. Any questions for Luana?
So I have one remark and one question. So let me start with the remark. So another area where graph neural networks are very useful is actually applications of machine learning to other areas of science, biology, let's say, where many, right, if you want to understand cancer, it's really important to understand the pathways, which are graphs, and you will have features which sort of maybe some properties of your nodes there, and then you have a network. And people use graph neural networks to sort of combine the features which are sitting on the vertices with the graph structure, a little bit like the talk we heard. That's the first talk in this series. And then a very theoretical question. When you showed this picture where you were blowing up or stretching the area near the origin of the spectrum, it sort of begs the question whether maybe there's an information theoretical bound where you just can't do better than a certain thing, because if you blow it up too much, then you just run against the unavoidable statistical error. And so there may be some square root of something which will put a bound on, you can't just have a better resolution. So I wonder whether you can comment on that.
Yeah, I do believe that that will happen, right? If you have like sparser graphs, because what I think happens if you have sparser graphs, right, is you could think that you could kind of like blow up the graphon model to the positive, like real plane. And so if you did that, even if, I guess, even if you still have a compact operator, well, you still, well, if the operator is not compact, then you're not going to have this accumulation of eigenvalues there. So it might be that, I mean, then we wouldn't be able to say what we say about this trade-off here, right? It is a product of this accumulation of eigenvalues close to zero. But I do think that the perturbation of these eigenvalues that you get from sampling graphs from your underlying graph model is kind of harder to model, right? It's more noisy. So there might be something happening there that would also kind of lead to this trade-off.
Okay, so let me just.
I have a very quick question on the transferability. I was wondering if you comment on the metric or like how they're like two graphs, how do we compare the, I mean, in general, how the transferability is defined. Is there a systematic way or just compare the output of two GNNs?
So
maybe repeat the question for this.
Okay, so what Joan is asking is how do we compare, essentially how do we compare outputs of GNNs on graphs of different sizes, right?
Yeah.
Okay, so what we do is we look at the, so we go back to the graphon. So we look at the graphon induced by that graph, which is kind of like a step function or a stochastic block model kind of type of graphon. And at the graphon signals induced by these graph signals. And then we take essentially the L2 norm of the difference between these signals.
Okay. Thank you. Yeah, let's take any other questions offline. So that brings us to the conclusion of this session, as well as the full series of talks and the event. So thanks to all the speakers. I think all the speakers did a great job to distill something really understandable and interesting for a wide audience in 10 minutes. I think the forum was really a success, at least for me. I got a lot out of the talks. So thanks everyone, and also for the audience who are here and who tuned in for attending and making this event a success. So thank you everyone. And yeah, it looks like the weather is back to the typical awesome we take for granted in Berkeley. So have a good weekend and thanks everyone.